Let's go. Okay, so we are doing gravitation this time around. Okay. G field is a topic which requires you to pull your knowledge from the first 6 chapters up to circular motion. So if you're uncertain of circular motion up till now, right, you better go and solve it ASAP. Okay, the picture you see there is the Curiosity rover. Okay, it is now stuck on Mars, exploring a very small area of Mars to prepare to let scientists learn more about Mars, so that in future when we destroy Earth, we can go ahead, move to Mars and then destroy Mars. Okay, that's humans for you. Okay, that's what we do. All right. Okay, let's move on. Okay, some of the concerns given to you for this topic. There's only one. Okay, mass of Earth and radius of Earth is not a fixed constant. Okay, the only equation given to you is there's a G missing. Gravitational potential is equal to Gm over R. Okay, we'll see that later. This notes there are some differences. Some of the tutorial solutions are given. Some of the example solutions are given to you. Those very wordy ones are given them to you, so you have a bit less to copy this time around. Okay. Okay, and these are contents. We will go through basically. We have 5 lecture slots. I'll be doing your first 2 points today. All right. Okay, so let's start. Okay, first thing we need to understand what is a field. Okay, right now your concept of forces, right, all involve objects in contact with each other. Be it be it your tension, be it your normal contact force, etc. All these forces require 2 objects to be in contact. If A pushes on B and B pushes on A, we know for sure before this part is that these two objects must be in contact with each other. Okay, so right now we introduce a field. Okay, a field is in a region of space where body experiences a force due to the presence of another body. No contact is needed. Okay, so this is very important. There are 3 main types of field you'll see in your syllabus. One is electrostatic field due to charge. Okay, 2 particles that are charged. Some of you have learned before. A positive charge will attract a negative charge. Positive will repel a positive. Okay, magnetic field, and then there's gravitational field. Each of the field, right, they have something particular that they act on. So for an object to be affected by G field, it must have a mass. For object to be attracted by electrostatic field, it must have a charge. For something to be affected by magnetic field, it must either be a magnet or it could be magnetized. Alright? Okay, or later you learn that actually moving electrical charges are also affected by a magnetic field. Alright, no context needed. That's the most important takeaway. Okay, and then we have, how many of you have seen the diagram on the right hand side before? Sec 3, Sec 4 got do before, right? You use the compass, a small compass to plot. Okay, so this are what we call field lines. Field lines do not exist in real life. Field lines what they represent is just simply the direction of the force acting on an object. So in this case, right, if your object is here at position 2, the field line is tangential through it. Okay, it's basically a tangent. Okay, so basically if you extend this field line here, right, this field line will go this way. Okay, that means at this tangent is this way. This is the direction of your force acting on the object due to the field. Okay, similarly, let's say you choose another point. Okay, you choose another point anywhere, you just need to draw the tangent to the field line there. Okay, spacing of the field line will tell you how strong the field is. Okay, which part of the magnet is the strongest? Near the poles, either side, right? Okay, so either side, you will have, that means at this point, your field lines will be very concentrated. Okay, because you know for sure that the magnetic field is the strongest around the ends of your bar magnet. Okay, field lines cannot intersect. Very, very important. Okay, because if you intersect field lines, this is what's going to happen. Okay, why can't field lines intersect? Okay, let me erase this. Okay. Okay, if you intersect, right, you mean that at the point intersection, let's say you place an object where let's say the G field, you place a mass at a point where two field lines will intersect each other. What's the direction of the force then? Would it take this way, or take this way, or would it settle for something in the middle? We don't know, right? Okay, so to rule out this fact, okay, your field is such that at any point of time, right, your force is only in a single direction. You cannot have two forces acting on the same object due to the same field. Alright? Okay. Okay, so we have roughly defined fields. So let's look at what's a gravitational field. It's a region where mass experiences a gravitational force. Okay? Any object that has a mass you place within a G field, it will be subject to a gravitational force. Okay, what causes a G field? In this case, right, okay, this is planet Earth. Okay, if I choose to place an object here, okay, we know for sure by this definition, this object will experience a force this way. Alright? So what causes the field? The Earth, right? The Earth is the source of the gravitational field. Okay? And later you'll learn that basically any object that has a mass can cause a field. Okay, that means two persons sitting next to each other are attracted to each other. Okay, I'm attracted to the projector right at the back of the room. The projector is also attracted to me. Okay, your one strand of hair is attracted to the other strand of hair. Not wrong to say that as well. Alright, we'll do more of this later. Okay, let's go on. Yeah, sounds a bit wrong, right? Attracted to each other. Okay, three kinds of field lines. Okay, we can treat the object as a point mass. I mean, it's just a dot. Okay, so if you have a dot, right? Okay, your field lines all converge towards the center of the dot. I haven't told you yet, but it's quite clear by now. Your field lines are all, your G field is an attractive field. That means if the Earth sets up the G field, everything within the G field is attracted towards Earth. Okay, so your field lines all converge at the source of the G field. Okay, so basically there are radial lines pointing towards the mass. Okay, if you have a spherical mass like this, we know Earth is not a point. Okay, but we can do this trick to assume. So what we do is that we assume that the source of Earth's mass is right at the center. And then if you just extrapolate all the lines in, right, you basically notice that the lines will all intersect nicely at the center as well. It is as if Earth is this way. You have a core mass here. Okay, this is the mass of Earth surrounded by a big shell around it. Okay, and then of course this is your radius of Earth. Okay, it's basically a small concentrated mass in the middle surrounded by a shell. Treat it this way, then it's easier for you to understand. Okay, for our syllabus, right, we are concerned about outside of Earth, not so much of within the Earth itself. Okay, so all this basically they run towards the center, they all point towards the center. Okay, but if we look close to the surface of Earth, okay, then we have another interpretation. Okay, because can you see the curvature of Earth with your naked eye? Not really, right? All you see is a flat ground, right? Okay, but then if you just zoom in all the way this picture here, right, all you get is that, imagine just this part is curved. This whole thing is curved. This is just one small part of the curve. Okay, the curve is always, okay, the field lines are always perpendicular to the surface. So if you zoom in closely, your field lines are all parallel. Okay, and you realize that the spacing is even. The spacing between them is even. So this one basically when we are close to the surface of Earth, right, we always assume that your G is close to what value? 9.81, right? This one you have seen before. Okay, only at the surface of Earth or close to it. How close is close? Later when we look at the radius of Earth, we can estimate what kind of values we can treat as close. Alright? Okay, let's go on. Okay, so field lines do not intersect. Oops. So this one you have done. Let's go on. Okay, first equation, you need to memorize this. Newton's law of gravitation. You cannot run away from Newton yet. Okay, it states that the attractive force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so if we look at this, this is the product of two masses here. I believe I have a diagram below. Okay, Here I'm using M, capital M and small m, but I just assume this is M1 and M2. Strike off the M's for you. Okay, so directly proportional to the product of the two masses. So you are saying that the gravitational force is directly proportional to M1, M2. Okay, and then you go on to say that is inversely proportional to the square of the separation. So I'm saying Fg is inversely proportional to 1 over r squared. You put these terms together, this is a constant. Okay, from these two terms, right, these two equations, I can say that your gravitational force is proportional to your m1, m2 product over r squared. But in order to put an equal sign, you need a constant there. Y is directly proportional to x, so y equals to kx, where k is a constant. Okay, then you ask what is the value of this constant. Okay, so this is what we have right now. This is the most fundamental equation you have in this part here. Okay. Okay. So once we have this, okay, all these are the terms. Okay. Take note of the units that we're using. Okay. Magnitude of your gravitational force is Newton. The unit is Newton. The point masses are to be substituted in kilograms. The separation is to be substituted in meters. And this is the constant that you have, your capital G. It's known as universal gravitational constant. 6.67 times 10 power negative 11 Newton meter square per kg square. Okay, you will do well to memorize this number. You will be using it all the time for this chapter. Okay. Notice that we didn't spend so much detail about the direction of the force, but just always note that it is an attractive force. Some textbooks will tell you that there's a negative sign here. Okay, the book is not wrong. It's just telling you that, remember, for vectors, if you treat your r as positive and the force is negative, it just shows you that your force is in the opposite direction. That means it's towards the source of the G field. Okay, your tutors will explain a bit more for you during tutorial. Okay. Okay, let's go on. Okay. So in this case, right, does it matter if I write M1 or M2 first? Mathematically, does it make a difference? No, right? M1 times M2, M2 times M1 is the same thing, right? And then sometimes you'll see questions giving you capital M and small m. Okay, it is the same. Okay, basically I just take two masses. The two masses involved, multiply them together. So let's say I have two students here. Let's say two boys sitting side by side. Both of them weigh about 70 kg. The attractive force is directly proportional to 70 times 70. Okay. The magnitude of the G force exerted on each point mass is the same and attractive in nature. So capital M pulls on small m with Fg, small m pulls on capital M with Fg. Same force. Which law am I trying to satisfy here? First law is the first law? Newton's which law? Third law, right? Remember when A acts on B, B must act on A with the same type of force, opposite direction and equal magnitude. Okay, so this is Newton's third law of action. Okay, so that means I can say that if Earth pulls on me with a certain G force, I'm also pulling on Earth with the same amount of G force. Okay. Okay, let's look at the first example here. I believe you have this as a blank. Okay, just let you have a chance to apply this equation. Okay, model of a black hole is a point mass of 6.0 times 1024 kg. What's the force on the point mass of 5 kg at a distance of 2 cm from this black hole? Okay, a black hole is basically a star that has collapsed. Okay, remember a star is very, very massive. Okay, but once it collapses, it becomes very, very, very small in terms of its radius. Okay, but it has the same mass. Okay, this is the basic understanding for black hole. Okay, what are the numbers that we should be concerned about here? What should we be concerned about? We have this mass. Okay, I can let this be M1. Okay, is that M2? This is M1, this is M2, right? Okay, what's the separation between them? 2.0 cm. Can I sub as 2.0 cm? No, I should sub as 0.02 meters. In fact, 0.020 meters. You should be a bit more precise now because you are starting on SPA. Okay, so let's look at the answer. Okay, so this is the diagram that we have, the same diagram. Of course, now this is 2.0 cm, and these are the units, these are the masses we have. Okay, so we just apply our equation directly. You plug in the values, okay, and then you get 5.0 times 10 power 18 newtons. Is that a big force or small force? Very, very big force. Okay. Okay, can let's go on. Okay, so answer is D because it was previously an MCQ. Okay, so again, I can still apply this same equation if I'm using spherical masses. I told you to just treat it as a small concentrated mass within the shell. So it basically becomes like this. So Earth, I can, in terms of calculation, I just treat it as this. Okay, so I can still apply my equation directly. Alright, so if I'm on the surface of Earth, let's say right now I'm here. I'm an object here. Okay, I'm affected by mass of Earth, but my distance is RE, radius of Earth, still attracted towards the center. Okay? Okay, so basically the unit, the notation just changed accordingly lah. As in your point masses now, we're talking about spherical masses, and then separation we are measuring from the center of the two spheres. Okay, center of the object, center from one center to one center. So this center to this center, and not the surface to the surface. Okay, be careful about that. Okay, so this is one. We still use the same equation. Nothing has changed. Okay, let's look at example 2. Example 2, I believe you don't have to copy. Alright? Okay, so on the ground, the gravitational force on the satellite is W. W is basically, you think about it, the weight of the satellite. Okay, right now I'm going to lift the satellite a bit higher off the ground, 0.02 R. Okay, it's off the ground now. Okay, where R is the radius of the Earth. Okay, first thing I can do is that I can write this equation first. Okay, consider Earth as a point mass in center. On the surface of Earth, right, my separation from the center of Earth is R, radius of Earth. Okay, so I can just apply G, capital M, and small m R squared. This M here, so let's just note down. M is mass of Earth, and then small m is your satellite. Okay, so I'm just applying the equation directly. G capital M times small m over R squared, and this will give me W as indicated by the question. Alright? Okay, right now you go higher. Which part of the equation will change? Will your capital M and small m change? No, which one will change? R. Your new R is what now? 1.02 R, right? Okay, let's just check. At a height of 0.02 R above the ground, my new separation from the center is now 1.02 R. R plus 0.02 R. That's my new distance from the center. Okay, then I'm doing a bit of manipulation. I take out the 1.02 square. So I have 1 to 1.02 square over here. This one here. And what I'm left with is your original GMM over R squared. which is effectively your W. Okay, so I take 1 over 1.02 square multiplied by W, I get 0.96 W. Okay, what does that tell you about your effective gravitational force as you go higher and higher? It goes lower, right? Because you look at this equation, if my R increases, right, my gravitational force will become smaller and smaller and smaller. So this will link to a point, that means eventually, if I go far away enough, right, there will be a point of R where my gravitational force becomes 0 or close to 0. Okay, this bear the fact in mind, it will be useful in the next few lectures. Okay, let me clear off the screen again. Okay, we're going to talk about something a bit more complicated now, neutral point. Okay, what exactly is a neutral point? Okay, let's say you have two masses involved now. In fact, you have three masses. You have M1, capital M1, capital M2. Okay, and then there's a small m right in the middle there, right? Okay, what must you have in order to cause a gravitational field? What must you have? Must you be as massive as Earth? No need, right? As long as you have a mass, you can cause a G field around you. You have an aura around you. Okay? So that means in this case, right, both A and B, they are attracting, they have a G field around them. There's one around A that is directed towards A, there's one around B that's directed towards B. In fact, if you want to think about it, there's also one around M as well. Okay? But let's just keep it simple. Okay. Consider the relationship between A and this small m, right? What's the direction of the force acting on small m due to A? Left or right? How would A act on this small m here? Attract or repel? Attract. So attracting must be always towards the left. Okay, so this small mass here, I have a force pointing towards the left. How about B? B will also try to attract small m, right? And pull it towards the right. So there are two forces acting on small m. Okay, one of it is due to A, the other one of it is due to B. Okay, so that means if I'm able to, okay, think about this. If I shift small m closer towards A, what will happen? Let's say my m now takes this position. Let's call this m, okay, let's call this m prime. What do you think will happen to the forces Fa and Fb? Which one will increase, which one will decrease? A will increase because now it's closer to A, B will decrease, right? Similarly, if I shift it to here, what will happen? B will increase, A will decrease. So that means if I'm able to find a point where the two forces are exactly equal to each other, what will the net force be? 0, thank you. Okay, so you are trying to find neutral point. That means you're trying to establish this point here where your two forces Fa and Fb are equal to each other. Okay, I'm going to draw for you I hope you remember your maths where you know that if it's 1 over r squared, your curve looks this way. Okay, this is here. Let's say the object is not here. Okay, if you draw the curve for force, it looks something like this. Go all the way down to here. Okay, so this is the force due to A at different distances. Sorry, I forgot to tell you this is the distance. Okay, it is negative because it is an attractive curve. Okay, I have no choice but to explain what I want now. Sorry. Okay, so if A is here, right? If object M is here, just quickly draw for you. If this is here, and the object in concern is here. Okay, the G field is caused by A. This is the displacement of the object from A. This is R. Let's call this R. This R is pointing to the right hand side. What's the direction of the attractive force? Towards the left. This is gravitational force due to A. Okay, because of vectors, right? These two must take negative. These two must be negative from each other. So my force on A exists below the x-axis, below the r-axis, right? Okay, for B, if you put it here, right? Okay, B, the force is towards the right hand side. Okay, so therefore, the curve is this way. The curve is this way for B. This is for FB. FB is pulling to the right hand side. Okay, so what I'm doing there, I'm just summing up these two curves. When I sum out these two curves, right, okay, I do a vector sum for them, I'll get the resultant curve to look something like this. Okay, this point here, this is your neutral point. Okay, where your forces will cancel out. Okay, we'll try example. I think there's an example there. Simple one. Okay, so so what's the equation that we're dealing with? Okay, I can write Fg on m by A equals to Fg on m by B. Okay, then just write the two equations out. Okay, so this is Gm1 over m over d1 squared equals to Gm2 over m over d times m over d2 squared. So make the necessary cancellations, you're left with this. Alright? No need to memorize this equation, just prove on the spot. Okay? So in order for you to, so we look at the next example. Can you see? You all have this in your notes, right? Don't have. On your page 7. Okay? Okay, let's look at this one here. Okay, mass of Earth is about 80 times the mass of Moon. At what position is it possible for the neutral point to be? Okay, recall at the neutral point, d1 square over d2 square equals to m1 over m2. That means, for you to find neutral point, right, the larger the mass, the further away you should be from that mass. Let's say m1 and m2. Let's say m2 is much larger than m1, which means that you should be further away from m2. You should be closer to the smaller mass. Okay, so if we consider both Moon and Earth, where do you think their neutral point will be? Just Moon and Earth. Would it be closer to Moon or closer to Earth? Closer to Moon, because Moon is more massive. That rules out C and D already. Okay, because C and D, they are closer to the Earth than to the Moon. Okay, you're left with A and B. Okay, which one is the answer? Okay, if there's no sun involved, if no sun involved, right, what's the answer? A. Because then it's just between Earth and the Moon together. Okay, if that's the case, right, then this one more or less, this is the neutral point between the Moon and Earth. Okay, but since right now, there's a sun involved, okay, so what do you think the sun will do? The sun will also want to attract. The sun is also trying to attract from this side. There will be a force acting towards the sun as well. So which answer do you think is correct? B. Okay. The graphs for this chapter is a bit counterintuitive, so tutorials will spend a bit more time talking about the graphs. Alright? So this is example 3. And the next one you have example 4. Okay, answer is B for this one. Okay, example 4. Okay. Point mass is located on the line joining the centers of the Sun and the Earth. How far from the Earth must the point mass be such that the gravitation pull of the Sun balances that of the Earth? The Sun is 1.49 times 10 power 11 meters away from the Earth, and its mass is 3.24 times 10 power 5 times the mass of the Earth. Okay, so what are the key numbers that we should take note of? There's only two numbers here, right? One of it is the total distance between Sun and Earth. This distance to this distance. Okay, the other one is that the mass of Sun, 3.24 times 10 power 5 times more. So I can say that capital ms over me is 3.24 times 10 power 5. Okay? Okay, I want to find a point such that it is neutral. No net force acting on the object is 0. So should we be closer to Earth or closer to the Sun? closer to Earth because Earth has a smaller mass. So I'm going to mark the distance away from the center of Earth to be r. Okay, that means this distance here, what is this distance? 1.49 times 10 power 11 minus r. Thank you. Okay, can Okay, any questions up to now? A lot, too much to answer. Okay, basically, right, I'm going to save you the time. You can write equation first. Okay, force from sun. This force acting on the object towards the sun should be equal to the force of Earth acting on the object because this is the neutral point. So I can write the equation as gms over m times 1.49 minus 10.11 minus r whole thing square, and then the same on the other side. Okay, you sub in the values. Okay, mass of sun, because of this equation, I can express the mass of sun as 3.24 times 10 power 5 times the mass of Earth. Okay, choose a theta. Okay, so that's why I sub this into here. Okay, in terms of mass of Earth. Why do I do that? So that I can cancel off. Okay, after this we end up with a very slightly complicated quadratic expression. Okay, I leave you to expand this term using your a minus b squared. A minus b squared, go and expand it. Okay, eventually your final answer should be 2.61 times 10 power 8 meters. Okay, can you leave some space in the middle for you to do this expression? Although your GC can key in directly, right? Can, right? You can key this whole equation in, right? And then work out what is the value of r. Yes or no? Let me just click for one slide first. I see what's okay. Actually, I'm done for today, but I'll talk about other stuff. Any questions? You can shoot now. Yes? Sorry? Which one? Can you repeat your question? I can't hear you. Oh, yeah. Yeah, sorry. This one should be meters. Yeah. I think I got confused myself. Okay, so actually I should be writing this as 1.49 times 10 power 11 meters. But in terms of the substitution, it's correct, right? Okay, thank you. Anyway, these two are equal to each other because I think I took it from the question directly. Sorry? Meters, huh? Your notes was it printed 1.49 times 10 power 8 meters of km? Oh, okay. Alright. Okay, I'll take the rest of the time. I will explain the part about the vectors again. I think that one we clear all the way, so have an easier path next. Okay, let's see here. Okay, let's look at this one now. Okay, let's say I have a source. I have a source of G field. Let's just draw it here. This is my capital M, and of course this is my small m. Okay, remember I always measure from the center of this one here. Okay, so if I were to draw the displacement vector of small m, right, it will be pointing to the right hand side. This is the displacement vector. Agree? My displacement vector is pointing to the right hand side. Okay, I'm going to treat the right hand side as positive. Okay, if you just consider the forces, right, what's the direction of the force? What is the direction of the gravitational force acting on small m? The force direction should be pointing towards small m. This is Fg. Correct? Okay? So if you look at this, right, if you look at r as a vector, okay, because this vector is pointing to the right hand side, therefore it is treated as a positive vector. For my Fg, if I treat this as a vector, it's pointing towards the left. Therefore, it must be a negative vector. So that's why some books, right, in fact, you want to be very particular, right? Your gravitational force is actually negative Gm over r squared. If I consider all of them as if I just treat it as a vector fraction 2. But in most cases, remember, this is just telling you the direction. Okay, as long as you recognize that it is pointing back towards the object, it's good enough. If you leave your answer, let's say you work it out, you never write negative sign, but you can tell me that this 10 newtons is directed towards the center of the earth, it's good enough. That means you must understand the direction of the force. Okay, let's go back to the graph again. Just on the graph that we are talking about, I realize you're a bit lost there. Let me just erase off everything. Okay, so I have this equation here. Okay, this is my gravitational force. This is my separation from the source. And I know that my equation is F in terms of vectors equals to negative G m over r squared. Okay, so if I were to make a displacement towards the right hand side, okay, this is a positive displacement because right now this is pointing to the right hand side. Okay, but my force will be pointing to the left. Again, I'm drawing the masses m and small m, even though the displacement is towards the right, but the force is towards the left. Okay, so therefore it exists below the axis instead. Okay, so if you were to look at this curve, right, this is basically an inverse square curve. It should look like this. Okay, it's below the x-axis because it is to tell you that when I make a positive displacement towards the right hand side, my force is always opposite direction towards the left. Okay? Then why is it just now the case, right, when you have another object here? Let's say right now you have another small mass here, this m. Okay, let's say another mass as this here, m2. Okay, m2 will, if the, oops, m1, m2, test mass in the middle. This is the force from 1. This is the force from 2. Okay, my displacement, I'm going to treat right hand side as positive. So right now, this is here. Okay, this curve is this way. This is for F1. In fact, it continues on. Continue on this way until it tends to 0. Okay, how about for M2? Would it be the same shape below? F2, right, is pulling to the right hand side. So that means it should be in terms of vector, it should be a positive number, right? So therefore, F2 should look like this. So, oops, sorry. something like this, all the way down. Okay, this F2. Okay, so be careful about that. Then you learn this, after you learn about potential, you flip one more time. Alright? Let me go back to the start for you. I'll just show you one quick video and we are done. Okay, so next week we don't have to watch video anymore. You know that this rover has a Twitter account and he takes selfies of himself. He has cameras over here. He can turn around to take a selfie. Okay, 6 views. Okay, so basically, right, the way they landed this thing on Mars, it was quite amazing, right? When you launched, I think in 2010, right, I was in school. I was in the staff room. Then I told my colleague, no, we must watch this video. Very important. Must watch. Dada must watch this video. Okay, so I just show you a quick simulation of how it landed. Let's see. I hope you've seen this before. Okay, so they flew to Mars. Took about almost 1 year to get to Mars. 1 year. You think Mars very near? Space is all about calculation. It's all about your maths and physics. Okay, so this thing here, this is almost above Mars. Let me just fast forward a bit. Okay, 8.5 months later, reach Mars. Okay, then this is the thing that's going to land on Mars. Looks like UFO. Okay, you see this because there is a lot, as you get closer to Mars, you have the atmosphere. It drags, slows down the object, slows down the thing. Okay. Yeah, so this material is designed to tahan a lot of heat, high temperature. Okay, now you see Mars. You are still about a few km above the surface of Mars. Then, boom, satellite. No, parachute open. Oh, sorry, balloon first. Yeah, they realized that the density of the Mars atmosphere is so low that you cannot just land parachute. It will be too fast. Then they have one more stage of rocket. Slowly lower it down. Still haven't finished. But if they realize they land like this, right, the rocket may cause damage to the rover, so cannot. So I think about 30 meters off the surface, right? Wow, this is the cool part. Very geeky, I know, sorry. The scientist did something crazy. They say, why don't we just lower it down using a crane line when the crane is floating in mid-air? They only try this on paper and computer simulation. Say maybe it will work. Okay, let's try. Okay, let's go. Okay, and they land. Okay, landed. Then this one goes off. Then now this poor rover left here forever. Okay, it can never ever come back. Okay. Okay, but anyway, this is the quite interesting. I'll try to bring a bit more space videos here so that at least you relate it to real life. Okay, thanks for focusing. Thank you. We'll see you on Friday.